Hello everyone, welcome to our tutorial that is based on combustion. Okay, today we're going to be looking at the burning of coke. So let me just read out the statement and then we can see how we go about dissecting and solving the problem at hand. So a furnace burns a coke containing 81% carbon, 0.8% hydrogen, and the rest is inert ash. The furnace uses 60% excess A. Okay, so A over and above that needed to burn all the carbon to carbon dioxide and hydrogen to water or water vapor. Calculate the moles of all the components in the flue gas if only 95% of the carbon goes to carbon dioxide and only 5% goes to carbon monoxide. So you can see now the one that produces carbon dioxide is a complete reaction, and then obviously the one that yields carbon monoxide is an incomplete reaction. So that has to be taken into account. And you're also given here the percentage excess A. Now remember that in combustion problems, oxygen is always in excess. Okay, so you take the fuel as your limiting reactant. That's very important. So now let's look at how do we determine the product gases. Now what you should also note, we're not told anything about a dry basis, or we're not told anything about offset analysis. So now you know that all the gas that actually leaves with the water vapor in one stream. So that's very key to note. So now the first thing that we do, we need to first sketch the problem. It's very important to sketch the problem so that you can easily understand and see which streams are coming into the combustion chamber and which streams are leaving the combustion chamber or the furnace. So I'm just going to do a little bit of a sketch here. Now we can see here, if we have something like that for our sketch, this is our combustion chamber. So there you've got your product, there you've got your feed, and just below you can have your airstream. So now you can say this is our product stream. In our product stream, there's a carbon dioxide is there being produced, carbon monoxide, and then obviously we'll have H2O. Okay, if there's any unreacted oxygen leaving with the other combustion gases. Now here, this is a furnace, so you can just write furnace here, and then we've got our A stream. Okay, so there's A here. There's A. A is composed of 21% oxygen and 79% nitrogen. Okay, you can total that. Gives you what? A molar total of 1. Remember, these are more fractions because oxygen, A and A is a gas. So you need to assume what? Molar percentages. So now our fuel is given in the statement. We are told that it's composed of the following. So in the fuel there, let's see, we've got C, which is 81%. Okay, and then we've got hydrogen, which is 0.8, and then we also have ash, inert ash, so which means it doesn't take part in the reaction. It's an inert. So the balance to that, because only given 81 and 0.8%, so 100 minus 81 plus 0.8 will give you the 18.2. Okay, so this is 100. So this is a mass percentage, since this is a solid fuel, which is coke. So now moving on, we need to write down our bases. Okay, so you can see now this here is our fuel. This is our fuel, remember. Okay, this here is the A. You can denote it using the A stream. Just bracket it like that, and this is A. It's the A stream. So P stands for product. So this is your product stream. Product. So now let's proceed now with the question. Let's look at our bases. What bases do we have? Our bases now, we are given here. It's very easy to see when we are given. We're given that our bases is 100. Okay, now we can take this as mass, 100 kilogram of Coke. Okay, it's 100 kilogram of Coke because it's a solid, so we assume a basis of mass. Now moving on, we need to write down our chemical reaction equations. That's very important. Okay, so our first reaction, we are told that Coke reacts with oxygen to give carbon dioxide. Okay, now this reaction is 95% complete as given in the statement. So this reaction here is 95%, goes to 95% completion. They say this one is the complete reaction. Then the second reaction, okay, so about that, we just remove that. The second reaction is given by Coke reacting with oxygen, giving us CO, and that is given in the statement that it's 5%. Okay, this is incomplete because it liberates carbon monoxide. Any reaction that liberates carbon monoxide, then you know that that reaction is incomplete, or it's partial combustion. And then our third reaction is the hydrogen that burns there. Now remember that hydrogen is a diatomic element in nature. So now when you write it in the equation here, it must be H2, not H, because it's a diatomic molecule. Okay, hydrogen gives us H2O. Okay, since we're not told anything about hydrogen, we assume that it goes to 100% completion. Okay, so it's a complete conversion process. Now you can see here that our equations are not balanced, so it's also important that you balance your equation. The first one is balanced, that's fine, but the second one, you can place a half there to balance it, and the third one as well, half. Then those equations are now balanced. Okay, then our equations are balanced. So this is how we start. Now you can see that we've got our sketch here. We can see which gases are supposed to be determined as expected in the question. Now you must place question marks here because that's what you're looking for, so that you remember what you are looking for. Okay, so all these gases are actually unknown. That's what we need to determine. So now moving forward, we can see that we are given the masses here in the F stream. Okay, that's a mass percentage. In the A stream, it's a molar fraction or mole percentage. In the P stream, since these are going to be gases, we're also expecting to get what? Mole percentages. So first of all, we must make sure everything is uniform. So we should convert these mass fractions to what? To moles. Okay, now since our basis is 100 kilograms, so we know 81% gives you 81 moles. 0.8 is 0.8 moles. Okay, but since hydrogen is diatomic, okay, we have to make use of the two atoms there when we do our conversion to moles. So let's look at that. So now you just move on and you write it neatly. F stream, get your F stream. So look at that. So you've got your F stream here, which is your feed stream or your fuel stream. Okay, so you've got a component there. You've got a component there. Look at this. You've got your F stream, you've got your component there. Sorry about that. So now you've got the component. So let's look at that. So components, you've got C, you've got H. Okay. Well, since it's diatomic, this is what you do. And then you've got ash. Ash, you know, it's 18.2. The other one is 0.8. The other one is 81. Now these are kilograms. Yes, these are kilograms because it's your mass. Okay. Now these kilograms total up to 100. They total up to 100. So here you're going to have 100. Okay. So now once you have the 100, you can go now and find your molecular weight. Molecular weight, you have it. It's 12 for carbon and it's 1 for hydrogen. Okay, the ash doesn't have a molecular weight. So you go and find your moles. Your moles is 6.75, and then 0.8 divided by 1. So this here, our molecular weight actually is supposed to be 2. So it's 2 because of the diatomic. So 1 times 2 of the atoms, you're going to get 2 for your molecular weight. So this then now gives us, if you go 0.8 divided by 2, you should get a very, very small number. Okay, yeah, it's 0.34. Okay, so now these are our moles. So now once we have converted everything to moles, we can proceed. Okay, so now what's the next step? Remember, what you are looking for is the product composition of this particular stream, the P stream. But now, in order for us to get that first, we need to know how many moles of carbon and of hydrogen have reacted, so that we know how many moles are produced of carbon dioxide, carbon monoxide, H2O, and also the oxygen and the nitrogen as well. So now we need to first find the moles reacting. Okay. So now, how do we get that? So for the first reaction, we know that the moles of C, or the moles of carbon, okay, that react, it's going to be given by the conversion. Okay, percentage conversion multiplied by the carbon that was initially fed, so C fed. Okay, so now our conversion is 95%, so 0.95 multiplied by 6.75, you get 6.41. Okay, yes, so 0.95 multiplied by 6.75. Now the 6.75 here, okay, 6.75 is what was initially charged in moles, but now you multiply it by the conversion, which is 95%, then you can be able to get the C that reacts. Okay, so now this is what we've done, conversion multiplied by the C that is fed, so it gives us 6.41 moles, because we've converted everything to moles. So these are moles. Okay, these are moles. So now we go back, and then now we can actually write the values here at the top, so that we know what we're talking about. So 6.41, sorry, 6.41, 6.41 is to 1, so 6.41, we use the molar ratios, is to 1, so 6.41, so 1 is to 1 is to 1. Okay, now we go to the second reaction, we go to the second equation as well, then we look at that. Okay, go to the second equation and we look at that. So if we have a look at the second equation, you can see that this one is the incomplete reaction. So before we can come and check, we must make sure that our reactants can be delivered. So let's go back here. So you've got C, that's for the second equation now. Second equation, C that reacts is given by, is the same formula, but now it's 0.05 multiplied by 0.05, just remove that, 0.05 multiplied by what initially came in as well. So now what initially came was 6.75. Then what do you get? 0.34 moles if you punch on your calculator. Okay, so now we know that 0.34 moles is the moles that are reacting in the second equation, because we've used the percentage conversion for the second equation, which yields carbon monoxide. So now if you go back, this is the second equation, 5%, the one that yields carbon monoxide. So we've got 0.34. Okay, so now we've got 0.34. Let me just remove that. Okay, 0.34 to 0.34 divided by 2. Okay, 0.17 and 0.34. Okay, so 1 is to 0.5 is to 1, or 1 is to half is to 1. You use the molar ratios. Okay, so now moving on. Now for hydrogen it's very easy because it's 100%. So now it means whatever comes in, it's what reacts. So the hydrogen that reacts, or the hydrogen that actually comes in, it's easier for us. It's 1.6. So it's 1.6. You're going to have 1.6, and then here is divided by 2. So you're going to have 0.8, and then lastly you're going to have 1.6. So 1 is to half is to 1. Okay, so now if you've got this, you can see these red values here. They're actually presenting the moles reacting, you see, on the left hand side. But now on the right hand side is the moles that are produced. This is the product side. Okay, so your 6.41 for carbon dioxide is moles produced. 0.34 for carbon monoxide is moles produced. 1.6 for H2O, it's the moles produced, of which means now we've actually found the amounts on the product side. So 6.41 is the one that is produced here on the product stream, and same thing applies to the carbon monoxide and H2O. So what we need to go and determine is the oxygen and the nitrogen. So going further now, let's go and find out how do we actually determine the oxygen and the nitrogen. What do we start with? What is very, very key at this moment now, it's for us to go and first utilize the percentage excess that we're given in the question. We're given that the percentage excess is 60%. So we can utilize that to actually get the oxygen entering. So now, let's just have a look at that. Okay, let's have a look at that. Let's move down and see percentage excess. So percentage excess is given by the oxygen coming into the system. Subtract the oxygen required for complete combustion. This is the oxygen required to react with the limiting reactant if the reaction were to go to completion. So it's a theoretical assumption. Okay, so now this over oxygen required to react with the required for complete combustion. Okay, so now when you have this, okay, this is multiplied by 100. Okay, or you can just leave it like that. In my case, to the sake of space. Okay, so now what do? In this equation, we have percentage excess. So what we need to go and find, is this oxygen required and oxygen required, and then we can find oxygen coming into the system. Okay, now oxygen required, it's easy to find it. Okay, so now what we need to do is just to apply the formula. So oxygen required for complete combustion is going to be given by the oxygen required for complete combustion in the first reaction and oxygen required in the second reaction. In the third reaction. We don't use the one in the second reaction. We only use the one in the third reaction. Okay, first and the third reaction. Now, why are we doing that? Let's just go to our list of equations. So remember now, initially I said 95%, then I wrote CC, I wrote IC and CC. This stands for complete combustion, CC. So that's the first reaction. And then IC is incomplete combustion, and the third one is complete combustion. Now the reason that we're eliminating this equation is because when you're calculating percentage XSA, it's based on a theoretical assumption. Okay, if the reaction were to go to 100% completion, okay, how would it look like? So how much oxygen would you utilize? Okay, so now that's why it's based on the first and the third reaction. So now let's just go back and see how do we get this oxygen required for complete combustion. Okay, so now our oxygen required for complete combustion and it's going to be given by, now we know in the first reaction we've got 6.75. okay, limiting the moles of the limiting reactant fed multiplied by the stoichiometric of the excess divided by the stoichiometric coefficient of the limiting. Okay, now because it's two of them, so plus moles of the limiting reactant fed in the third equation, which is 1.6, multiplied by the stoichiometric coefficient of the excess divided by the coefficient of the limiting, which is 1. Okay, so it stays as is. Now you can actually sum up this. Okay, so your total is 7.55 moles. Now this is the oxygen required to react with the limiting reactant if the reaction were to go to completion. As I mentioned earlier, it's a theoretical assumption. It's not the actual oxygen that reacts when the combustion process takes place. It's just a theoretical assumption that helps us to actually find the oxygen coming into the system, or the percentage excess. So now we can easily substitute in this previous equation. So the 7.55 can be substituted in this equation so that we can go and get the oxygen coming in. Okay, remember we've got 3 unknowns, so now we found oxygen required, so we only have 1 unknown, which is the oxygen coming in, and that's what we are looking for. Okay, so now we go and substitute. We say that 60%, we have 0.6, the equation oxygen coming in, subtract oxygen required 7.55 all over 7.55. Okay, so our oxygen coming into the system is going to be given by that, which yields 12.08 moles. Okay, you punch that in your calculator. So this is the oxygen entering the system, and remember the oxygen is entering the system or the furnace in stream A. Okay, so the oxygen that is coming in through stream A, this oxygen here is 12.08. That's the oxygen that is coming into the furnace. So that's why it's very important to sketch, because you can always refer to your diagram and see if things make sense. So the oxygen coming in is the oxygen that we've just calculated. Now things become easier. Now if you know how much oxygen you have, okay, now it's easier to actually utilize. Okay, so let's go back and look at the statement now. Okay, so this is what we've calculated, 12.08 moles oxygen coming in. Now we need to find, since we know that oxygen is 12.08, now we can use that knowledge. Remember the mole fraction of oxygen in air, or the composition of oxygen in air, is 21%. Okay, so if 21% of air is equals to the oxygen coming in, okay, then how much is air? So now we want to find air. So we know oxygen coming is 12.08. So which means air, how much does it give us? 57.52. Yes, we use the calculator. 52 moles, and it makes sense because you can see that the airstream has to have a bigger value than the oxygen. So now if you see that your oxygen is more than the airstream itself, then you know that there must be a mistake somewhere. You just go back and check your steps. And then now let's go and determine the nitrogen. Since we have the total airstream, which is 57.52 moles, what about the nitrogen in A? Nitrogen in A is going to be 79% of A. Okay, 79% of A, so it's 57.52 multiplied by 0.79, and what do we get? 45.44. 45.44. Okay, these are moles. These are moles. Okay, that one there might not be clear. Okay, so we just need to try and write it neatly, much better. Okay, now moving forward, we just got the oxygen coming into the system and we've got the nitrogen coming into the system. But you know what's important? It's for us to find the oxygen produced and the nitrogen produced, because that's what the question wants. So it's very important to always know what you are looking for. Okay, remember we have determined carbon dioxide, carbon monoxide, and water vapor that is liberated in the process. But now what's remaining is that we determine the oxygen. Now it's very easy, since you know, we can start with the nitrogen itself. Now nitrogen is in the nitrogen in stream A is equivalent to the nitrogen in P. Okay, why? Because nitrogen is an inert, it doesn't partake in the reaction. We also call it a tie component. Okay, it's a tie component. Okay, because it just goes into the furnace and leaves. It is assumed that it doesn't take part in the reaction process. Okay, obviously practically that is not entirely true, but it's a negligible fact as far as a theoretical aspect are concerned. Okay, so now let's look at how we can determine the airstream. So if this is true, then we know that our nitrogen produced is going to be the same, so it's going to be 45.44. Okay, now moving forward, let's go and find our oxygen. Okay, oxygen produced, how do we determine that? It's not tricky as well. Oxygen produced is the oxygen that is coming in A. Oxygen that comes in A. Subtract oxygen that reacts. Remember, oxygen coming in A is the oxygen that is coming into the system. So now we do know the oxygen coming in A is 12.08. Subtract. Now the oxygen that reacts, we take into account all the reactions now. Unlike when we are calculating the oxygen required for complete combustion, we take into account all the reactions. So which means now when we calculate the oxygen required, the oxygen that reacts, we're going to take into account the first reaction, second reaction, all of them now. So we take into account this reaction, and that reaction. Okay, This is the oxygen that reacts in all these equations. This is the oxygen that reacts. You've got this one reacting, that one reacting, and that one reacting. So it's 6.41 plus 0.17 plus 0.8. Okay, you sum up all the three. But now when you're calculating for oxygen required like we did before, you only focus on the complete combustion processes, which is equation 1 and equation 3. Okay, so I think that's straight to the point. So now let's move forward. Okay, move forward now. Let me just go down, and then so that we can sum up the whole process. So now oxygen that reacts in the first equation, second equation, and third equation. So we've been given the values. Okay, so you just write them down and sum them up. 6.41 plus the other one is 0.17 plus 0.8. Okay, and then you get 4.7 moles. So this is the oxygen unreacted. It's 4.7. That's why it's recovered on the product side. So this is the oxygen that is produced, or the oxygen unreacted. That's very important to know. Okay, so now once you've done that, you are almost done. What's left is just that you need to write down the product composition. Okay, because you are required to put this in percentages or mole fractions. So the product composition now, you just tabulate it. Okay, you can have your component here. So a component, okay, which is carbon dioxide, H2O, water vapor, carbon monoxide, oxygen, and nitrogen. Okay, and then here you're gonna have your total, and then you've got your amount of moles, kilogram moles. Okay, so we've got 6.41, 1.6, these are the amounts, 0.34, 4.7. Oh, sorry about that. We'll remove that before it gets confusing. 4.7, and then the last one is 45.44. Okay, so you total this up, comes up to 58.49. Okay, now that you have that, you can go on to find your mole fraction. Okay, you can just go on and find your mole fractions. Okay, so your mole fraction here, so 6.41 divided by 58.49, that's the mole fraction you get. 96. Do the same thing for water, for H2O. 1.6 divided by 58.49, you get the 0.0274. Do the same thing with carbon monoxide, then you get 0.0058, and then this one, oxygen, becomes 0.804, and lastly you've got 0.7769. Okay, and then you can total that. Okay, more or less the total, and then it's your mole percentages now. Okay, so your mole percentages, it's the same, you just multiply by 100, so it's 10.96. H2O is 2.74. The other one is 0.58. So it's in very minute quantities. Then the other one, lastly, you've got 0.08. So this is supposed to be 8%. Shouldn't write it in molar form. I should write it now in percentage form, not in mole fraction. Sorry. So now here you've got 8.04, and then 77.69, nitrogen being in large quantities, and this is your 100%. So this is your product gas composition. Okay, this is your gas composition. So this is your P stream. Okay, this is your P stream. So you've got the total of your P stream. So you've represented, or you've actually determined the product gas composition, and this is what you were supposed to go and determine. So now if you look at the gas analysis, you can actually see this is the flue gas analysis that we've determined here. You can actually see that carbon dioxide is 10.96 and H2O, which is water vapor, is 2.74. Carbon monoxide, very minute quantity, 0.58, and obviously oxygen and nitrogen being in abundance. Now you can go back and check the steps that we've actually gone through, but what's really important is to keep in mind, or bear in mind, what is it that is being asked in the question. So like in this example, what was very important is to take note of the conversions, the 95% and the 5%, because that's where you will actually know and be guided how many equations that you need. Okay, what is burning and the elements of it. Okay, so this question is a very interesting question, very synonymous to rigorous core problems. So next time now, because in this question you can see that we didn't have any OSAT analysis, we didn't have a refuse where the ash has to leave the system. So now we'll check next time as to how do we calculate that if we take into account the ash and the carbon that leaves with the ash. How does it go? So now we'll conduct the elemental balance in the next lesson. Thank you.